from the basics of material science and engineering, the first unit, crystallography or crystal structure. From the first unit, crystallography or crystal structure. Okay. There is a chance to ask one or two questions, one question or two questions. Mostly two questions every year they ask. More weightage is there this topic, right? So I'll explain first different bonds, different types of bonds in a simple way because we don't have time to write everything. That's why I'll consider the table of all these bonds. Okay, this is very small, right? So I'll consider in the second page. Okay, now see here. There are three important bonds. There may be a chance to ask question from these three important bonds. One is ionic bond, second is covalent bond, third is metallic bond, and also a secondary bonds are there, van der Waals bonds. So if you consider the bond strength, ionic bonds are strong and covalent bonds are also very strong, but metallic bonds are also strong, but that depends on the material. Some of the materials are weak, like lead, aluminum, these materials. Van der Waals bonds are very weak. And mechanical properties of these ionic and covalent bond materials are hard and brittle material, but very less ductile material. But these metallic materials are, some of these metallic materials are good hard, and but they are having good ductile materials also, good ductile and malleable. And electrical point of view, we consider ionic materials are poor electrical materials, right? They won't allow the flow of electrons, but they allow the flow of ions. In the question, in this case, you can take a flow of ions, it is possible, right? And covalent bonded materials are also completely insulators. Insulators are otherwise semiconducting materials, and metals are very good conductors by the transport of electrons from one place to the place. And insulators and van der Waals are also insulators in both solid and liquid states. Van der Waals are also insulators in the solid and liquid state. I'll explain ductility and malleability later, okay? Right? And thermal properties, if you consider, the melting point temperature of ionic materials and covalent materials are very high. But metals, it depends on the metal. Like some of the metals are having very high, and some of the metals are having low melting point temperature. And van der Waals bond materials are having very low melting point temperature. Melting point temperature, right? That you have to remember. Solubility important. Soluble in polar solvents. See, ionic materials are soluble in polar solvents like water. Ionic solvents are soluble. And but covalent materials are very low solubility. It means not all covalent bonded materials are soluble. Some of the covalent bonded materials only soluble. And remember, very important thing: metals are insoluble in polar solids or water. Metal can't soluble in water, but metal soluble in acids or some alkaline chemical agents, right? And van der Waals bonds are soluble in organic solvents, like different solutions it is going to make. And structural point of view, we consider the structural point of view. We consider this is very, very important. The ionic bond materials are not directional. Ionic bond materials are not directional, but covalent bond materials are highly directional. Non-directional. Only covalent bonded materials are directional. Remaining all are non-directional bonds are present. Randomly bonds are present. Okay, now so because of these non-directional bonds, okay, the coordination number is very high. But here the coordination number is low in the covalent bond material because they are highly directional bonds are present. Even in the metal also non-directional. In the van der Waals bonds are also non-directional. Remember, covalent bonded materials are highly directional. Okay, highly directional, right? And examples of covalent bond materials, you can take a diamond, right? Diamond. And examples of van der Waals bond materials are NaCl, CaCO3, and metals are copper, iodine, organic components. I already explained this one anyhow, but I'm giving the table of this because there may be a chance to ask one question from this table. There may be a chance to ask one question from this table that I'm giving. Ionic bond, covalent bond, metallic bond. You have to remember these three. In ionic bond, the bond is going to form by complete transfer of electrons. And in covalent bond and metallic bond, the bond is going to form by sharing of electrons. Okay, now only covalent bond materials are directional. Ionic bond, metallic bonds are non-directional, right? And mechanical properties, if you consider for ionic material and covalent material, more or less they are same, very hard and brittle, but metallic materials are good ductile in nature. Electrical properties, if you consider, ionic materials are poor conductors, but they allow the flow of ions. Ionic conductivity is present in the ionic material, but covalent bond materials are insulators. Right? These things you have to remember. Okay. So in the previous year, one question they asked from these bonds, especially from the covalent bond. That's why I'm giving the table. Next, another important thing is for your exam, there may be a chance to ask the question from the Bravi's lattice systems. I explained 7 lattice systems, right? Bravi's lattice system, total 14. Total number of lattice systems are 14. Out of these 14, basic systems are 7. So you have to go through these 7 lattice systems also before going to the exam. This one. You have to go through these 7 lattice systems also before going to the exam. Okay, you have to go through these 7 lattice systems. Out of these 7 lattice systems, you remember just 5 because it is an objective paper, right? Objective paper means 4 options they are already given, so easy to eliminate. What are the things you can easily remember? Triclinic structure. Why it is? Why you can remember easily triclinic? All the angles are different. Alpha, beta, gamma are different. Like A is not equal to B is not equal to C. Alpha is not equal to beta is not equal to gamma. Remember this. And opposite to the triclinic, remember cubic. Because for cubic, A is equal to B is equal to C, right? A is equal to B is equal to C, and alpha is equal to beta is equal to gamma. 2. Remember these 2. Then third one, tetragonal. Tetragonal. I gave an example of what? What example I gave? Tetragonal. RTC bus I gave. RTC bus I gave. That means 2 sides are same, 1 side is different, right? That means A is equal to B but not equal to C, and all the angles are same. And orthorhombic, I said matchbox. Orthorhombic, I said matchbox. All the sides are different in length. Alpha, beta, gamma is not same, but angles are same, and they are 90. So 4 is over. And even if you want to remember, you can remember monoclinic also. Monoclinic is what? Mono means 1, right? Only one angle is different. Other 2 angles are 90, right? Remaining is same. A is not equal to B is not equal to C. And two angles are 90, they are equal to 90, but one angle is different. That's it. Remember 5 Bravis lattice system before going to the exam. There may be a chance. Just 5, no need to remember 7. Right? Next, from the structures also, they asked a question last year, last 3 years, every year one question they asked, mostly atomic packing factor of simple cubic. Last year question, the atomic packing factor of a simple cubic structure. 4 options given, very easy one. And in 2018 or 17, the relationship between lattice parameter A and R in FCC. This type of things they are given, so that I'll give you types of structures. First one is simple cubic structure. Now listen, in simple cubic structure, 8 atoms at 8 corners. This is basic one I'm giving, okay, in simple way, because we should cover all things in 3 hours, right? And effective number of atoms are how many? At each corner 1 by 8, like that 1 atom, like that 8 corners, so that effective number of atoms are 1. And relationship between R and A, is what? A is equal to 2R, you remember. I'll give you PDF of revision class, okay? I'll give you PDF of revision class, don't worry. Otherwise, take screenshots of all these things, right? Relationship between R and A is equal to 2R, right? Now, atomic packing factor or packing density. Atomic packing factor or packing density means what? Total volume of atoms in the unit cell. Total volume of atoms in the unit cell. Total volume of atoms in the unit cell by volume of unit cell. Okay. So what is the atomic packing factor for simple cubic structure? 0.52. 0.52. And empty space is 48%. I am not giving that one here. And coordination number. Coordination number is what? Number of nearest neighboring atoms or touching atoms. So coordination number is 6. Example is only one. You don't need to remember. That is polonium. That's it. In IS 2018 or 17, I don't know exactly. XIS question. This is simple, easy question they asked. 0.52. Okay. The atomic packing factor of simple cubic. Even 5.2 is not even 5. 0.5, 0.68, 0.7. Like that they are given. 0.5 is the answer. Right. And the second question is, body-centered cubic structure. Body-centered cubic BCC structure. Now in BCC, how the atoms are arranged? 8 atoms at corner and 1 atom at body center. 8 atoms at corner and 1 atom at the body center. Now the effective number of atoms are how many? At each corner 1 by 8, like that 8 corner, 1 atom at the body center, so the 2 atoms. And relations between R and A, if you take, what is this relation? Important for your exam. 4R is equal to root 3A. 4R is equal to root 3A. And atomic packing factor of BCC is 0.68. Empty space is 32%. And coordination number for this BCC structure is 8. And examples of this BCC structure is, I gave an example of disco, that is tungsten, iron, sodium, chrome. You have to remember this one. Body-centered cubic structure BCC. Next, third one is face-centered cubic structure. Face-centered cubic structure FCC. Okay. In FCC, how the atoms are arranged? 8 atoms at 8 corners and 6 atoms at centers of 6 faces. The effective number of atoms in the FCC, 1 by 8 at each corner, like that 8 corners, 1 by 2 at each face center, like that 6 face center, so that effective number of atoms here it is 4. Right? And relationship between R and A, that is 4R is equal to root 2A. This is one XIS question. Prelims. In 2018, I think so. In prelims 2018, they asked this question. Right? Relationship between R and A. Then atomic packing factor of face-centered cubic structure is 0.74. Atomic packing factor of face-centered cubic structure is 0.74. And coordination number is 12. And examples, if you consider NALCO, that is nickel, aluminum, copper. And also I said noble metals. All noble metals comes under the structure only, FCC structure. All noble metals. What are those? Gold, silver, platinum, palladium, like that. All these comes under the face-centered cubic structure. Right? This is the information about FCC. Next, fourth one is diamond cubic structure. Diamond cubic, otherwise tetragonal structure. Sorry, tetrahedral, not tetragonal. Tetrahedral means what? Tetrahedral means what? One atom surrounded by how many atoms? 4 atoms. One atom surrounded by 4 atoms. Now see here. In diamond cubic structure, how the atoms are arranged? See, 8 atoms at 8 corners, 6 atoms at 6 face centers, and 4 atoms inside unit cell on body diagonals of A by 4, A by 4, A by 4 coordinate. Okay, now 8 atoms at 8 corners, 6 atoms at 6 face center, 4 atoms inside the unit cell on the body diagonals of A by 4, A by 4, A by 4 coordinate from the corner. Now, the effective number of atoms present inside in this unit cell, how many? At each corner, 8, like that 8 corners. at each phase center 1 by 2, like that 6 phase center, 4 atoms inside the unit cell. So the total effective number of atoms are 8. See, this is effective number of atoms, not the total number of atoms required to form the structure. The total number of atoms required to form the structure is different, just to count the number of atoms. In diamond cubic structure, the total number of atoms required to form the structure is how much? Some 18. In FCC how many? 14. 8 plus 6, 14. In BCC how many? 9. In simple cubic, 8. Like that. Then relationship between R and A. If you take, that is 8R is equal to root 3A. 8R is equal to root 3A. And atomic packing factor of this diamond cubic structure is 0.34. Remember, lowest. What is the reason why it is lowest? Assertion reason, statement question. Why it is lowest? Because of tetrahedral arrangement of atoms. Tetrahedral arrangement of atoms. Because of tetrahedral arrangement of atoms, this is having low atomic packing factor, high empty space. And finally, coordination number, that is equal to 4. Coordination number, that is equal to 4. Examples of this diamond cubic structure is diamond, silicon, germanium. And also one more important thing you have to remember, zinc blend. It is a ceramic structure, that is a zinc sulfide. Zinc blend structure is also same as diamond cubic structure. The example for the zinc blend structure is compounds of third group and fifth group elements. Very, very important for electrical and electronics, especially electronics. It's a compound semiconductor is going to form. Germanium, arsenic, gallium, arsenic comes under this category. Gallium arsenic structure is zinc blend. Because zinc blend structure is compounds of third group and fifth group elements. In zinc blend structure, 8 zinc atoms at 8 corners, 6 zinc atoms at 6 phase center, 4 sulfur atoms inside the unit cell. Same parameters. That's why I'm giving zinc blend structure here. Very important, zinc blend. Listen carefully. Sometimes this zinc blend structure is also known as urgite. WURZITE, urgite structure. Don't confuse. Zinc blend structure or urgite structure, same. Okay, now this is the information about zinc blend structure. What is this? You should have calculated last slides. Okay. Gallium arsenic comes under this structure, diamond cubic structure, zinc blend structure, urgite. Right. And the fifth one is hexagonal close packed HCP structure. Now in hexagonal close packed structure, how the atoms are arranged? Tell me. See, very simple. There are 12 atoms, not 8 atoms. 12 atoms at 12 corners and 2 atoms at 2 base planes and 3 more atoms at the middle inside. 3 more atoms are middle at inside, right? Right. So effective number of atoms, how many? Tell me here. At each corner, it is not 1 by 8 fraction, it is 1 by 6 fraction. Like that, 12 corners plus 2 base center. At each base center, half of the atom is present inside the unit cell. Plus 3 more atoms inside the unit cell. So total number of atoms are 6. Okay, in hexagonal close packed structure, total number of atoms are 6. Now, relationship between R, A, C. We should consider C also here because it is not a cube, it is hexagonal. So C also valid. So for this, A is equal to 2R is 1. A is equal to 2R is 1. And C by A is equal to root of 8 by 3. Otherwise, 1.634. Remember, this is important for exam. Prelims. Direct question they will ask you for your exam sometimes. You have to remember. Direct question they will ask you. C by A is equal to root of 8 by 3. That is 1.634. Then atomic packing factor, that is equal to 0.74, same as FCC. So empty space is 0.26. Then coordination number is 12. And finally, examples of this hexagonal close packed structure is zinc, cadmium, beryllium, zirconium, magnesium, titanium. Just remember suffix mium, but don't consider aluminum, sodium like that. Okay, now? So these are the 5 structures you have to remember. I'll give you guarantee 1 question from these 5 structures, 2 marks. Easy questions, direct questions they will ask you from these 5. Okay, now 1 question is over. Next is crystallographic directions. They may not ask. That is a diagram, not diagram required. So in the paper, they may not draw the diagram either in the question or in the answer. But there may be a chance to ask a question from the Miller indices. There may be a chance to ask the question from the Miller indices. Either they will give you diagram or otherwise plain fractions they will give you. They will ask you what is the Miller indices. Understand? So for example, listen carefully. I'll consider a question of this Miller indices. Okay. Just consider this is a plane. Okay. Like this. So listen carefully. Sometimes in the exam paper, they may not draw the diagram, either in the solution or question. Indirectly, they will give you that plane fractions in x direction a by 2, y direction. Here it is a by 4 now, but it is not the length. It is the length you have to take. That is 3a by 4. And in z direction it is a. Like this, they will give you. They will ask you what are the Miller indices. A is the lattice parameter. Then Plane fractions are like 1 by 2, 3 by 4, 1. And reciprocals, if you take 2, 4 by 3, 1. Then Miller indices are 6, 4, 3. Understand? Sometimes they may not give you diagram. They will give you, instead of diagram, they will give you plane dimensions. The plane fractions for a particular given plane in a cubic structure is like so and so. What are the Miller indices? This type of questions they will ask you. So if you want to calculate Miller indices, what are the steps? First, you should locate origin x, y, z in the case if the diagram is given. Then measure the dimensions of the plane from the diagram. Sometimes listen carefully. Unplaned length they'll give you. Be careful there. Sometimes if they won't give diagram, directly they'll give you like this. Very easy. Take the plane fractions and reciprocate them. Convert into complete integer. Convert reciprocals into complete integers. Convert reciprocals into complete integers. That is important. Okay, now go through the Miller indices. Listen carefully. Go through the Miller indices. Miller indices represented with normal brackets. With normal brackets, that is important. Then after that, these things are also important. Like linear density formula in IS 2020, I think they asked this question. Linear density, basic definition. That is number of atoms in a direction. Linear means line. So number of atoms in a direction by length of direction. Number of atoms in a direction by length of direction. And also sometimes, mostly they will ask you direct formula. Okay, now sometimes they will ask you numericals also, simple numericals. Like if they ask you numericals, you should remember these things. If the direction starts from the center, you should take 1 by 2. The direction covers complete atom, complete passing through the atom and covers center 1. If the direction is not passing through the center, don't take 0. Okay, now listen, in a simple way, I will give you a hint. Direction represented with a square bracket. If it is 1, 0, 0, side length of the unit cell. Side length of unit cell, remember, imagine. Then if it is 1, 1, 0 or 1, 0, 1, 0, 1, 1, phase diagonal of unit cell. Phase diagonal of unit cell. If it is 1, 1, body diagonal of unit cell. Body diagonal of unit cell. Now listen. Number of atoms in this direction. In simple cubic. Number of atoms in BCC. Number of atoms in FCC. Tell me. Once if you know this one, very easy. Number of atoms in simple cubic 1, 0, 0. Corner, half, 1 atom. In 1, 1, 0. Corner, half atom, 1 atom. In body diagonal also 1. In the BCC, 2 corner atoms 1. Phase diagonal also 1. But body diagonal 2. In FCC, side length 1. Phase diagonal 2. Body diagonal 1. And length in the denominator, length of the direction you take. In terms of A, you can take A, root 2A, root 3A. Or more than enough. In case if they ask you problems related to this, remember the table. In 1, 0, 0, linear density, simple cubic 1 by A, BCC 1 by A, FCC 1 by A, like that. You remember this. Rahul Sharma, you didn't understand? Other people understand or not? Getting now? This table getting or not? Okay, in a simple way I'm giving this because sometimes you don't have time to draw the diagram, all these things. Rahul Sharma and Manisha, you just ask me after the class because we have very limited hours, so that I can't explain these things. It's not easy one. It takes some 3 hours, 2 hours like that. I'll explain briefly later after completion of the class because other people know this one. Okay, now? Right. So this is the information about linear density. So if line vector is not passing through the center, then we should some value. No, you should not take the value. Neglect that one, take it as a 0. If the line vector is not passing through the center of the atom, not only in the linear density directions, but also in the planes. If the plane or a direction, if it is not passing through the center of the atom, neglect it, take it as a 0. Right? Okay, now? Right. Next is planar density. Planar density, that is equal to number of atoms in a plane. Number of atoms in a plane by area of plane. Number of atoms in a plane by area of plane. Now see here, this is the atom, and if the plane covers this complete atom, then take it as a 1. Now this is an atom, the plane covers only half of the atom, then take it as a 2. If this is an atom, the plane is passing through the atom, but it is not passing through the center of the atom, then take it as a 0. Take it as a 0. Okay, now? So mostly remember the formula, and sometimes they'll ask you numericals also. So numericals also, I'll prepare a table of same as like that. 1, 0, 0, side length. 1, 1, 0, phase diagonal. And 1, 1, body diagonal. From these 3 only they will ask you numericals. Okay, now? Very simple numericals they'll ask you because it is there common for all branches, civil, mechanical, electrical, electronics. Right, that's why. So very simple questions they will ask you for your exam. Now, number of atoms in simple cubic, number of atoms in BCC, number of atoms in FCC. In simple cubic, in a plane, tell me how many atoms are there in the plane in simple cubic? At each corner, 1/4 of the atom, so 1 atom. And in the phase diagonal, phase plane, sorry, very, not. It is not. Okay, I'll write side plane, I'll write. See, this is a side plane. This is face diagonal plane. Correct, correct. And this is a triangle. Triangle. Okay, it is like this. It is like this. It is a square like that. So the number of atoms in the plane of 100 in simple cubic is 1. In BCC is also 1. In FCC it is 2. Because in the face one atom is there. Complete one atom. If you consider the face diagonal plane, means a rectangle if you consider simple cubic 1. In the body center 2. And in the face center also here is off, so 2. And in the triangle if you take here it is how many at each corner 1 by 6, 1 by 6, 1 by 6. That is 3 by 6. That is 1 by 2. Right? And here also don't take it as a body center atom is at the center of the triangle, so it is not present. So here also 1 by 2. And if you take triangle here 1 by 2 and 3 into 1 by 2, that is 2. Sorry, 2 here. And area if you consider, plane is a square, a into root 2a. This is triangle is root 3 by 4 into root 2a whole square. Side length is root 2a. This length is root 2a. This length is root 2a. This length is root 2a. Remember this table. Is there any mistakes? Please tell me if there is any mistake because I'm in fast now. 110 FCC have 1. 110 FCC have 1. Net problem is not there. From my side, net problem is not there. Please there. I think from your side only. 110 is not 1. In 110 FCC, it is there like this. 1 by 2, 1 by 2, 1 by 2, 1 by 2. Okay. 1 by 2, 1 by 2, 1. This is 1 and this is 1. 2 only, na? 110 FCC 2. And wait. Okay, sorry. Yes, right. This is a diagonal. Here it is not there, na? This atom. Wait. I think 2 only, na? Wait there. 2, na? 2 only. Not 1. Second one is 1 by 2. Which second one? Prabhakar Rao. What is 110? Anonymous attendee. What is 110? I can't explain now here. Anonymous attendee. What is 110? I can't explain here. Okay, now I'm going from this table. So second one is 1 by 2 on top, sir. Second diagram. Oh, yes, it is 1 by 2. Correct. Okay. Right. This is the information about planar density formula and planar density problems. This is the information about linear density formula and problem. See, from these three diagrams, these three directions 100, 110, 1, and simple cubic, this is FCC only. They'll ask you. They won't go diamond cubic, HCD. Okay, na? Right. So linear density and planar density is over. Next, interplanar spacing. Interplanar spacing formula concept. Just remember the formula, that is important. Actually, D is equal to 1 by root of h by a whole square plus k by b whole square plus l by c whole square. This is the general formula. But you don't need to remember the general formula. But interplanar spacing of cube, you remember. Cube only. Right? So cube A is equal to B is equal to C. By substituting that, you will get A by root of h square plus k square plus l square. Here HKL are Miller indices. A is lattice parameter. A is lattice parameter and HKL are Miller indices. You just go to that, you will get. And X-ray diffraction. X-ray diffraction method. Okay, na? Either numerical they will ask you, or otherwise direct formula they will ask you. X-ray diffraction, it is also known as Bragg's law. Okay, it is also known as Bragg's law. That is n lambda is equal to 2d sin theta. Yes. N is 1, 2, 3 like that. In case if n is not given, take it as 1. Order of reflection, that is, if it is not given, take it as 1. Lambda is the wavelength of the X-rays. Wavelength of the X-rays they will give you. D is interplanar spacing they will give you. Or otherwise you will get from the previous question, previous formula. Okay. And theta is Bragg's angle. Remember one important thing I'll tell you. In case in exam paper Bragg's angle what is given, directly you can take it as a theta. In case in exam paper if they are given diffraction angle. In case in exam paper if they are given diffraction angle, that means 2 theta. Like in exam paper if they are given diffraction angle to 60 degrees. Means don't take it as a theta 60. 2 theta is 60. Then only will get the answer. Don't consider. In a simple way, give a hint. Diffraction D double. Okay, na? Diffraction D double. So X-ray diffraction formula you have to remember. Sometimes numericals also they will ask you from this X-ray diffraction method. And lambda is equal to 2d sin theta. You have to remember. And lambda is equal to 2d sin theta. You have to remember. That is next. Next is defects. There is a chance to ask a question from the defect also. And one defect they asked in the last year, Schottky defect, basic definition of the Schottky defect. That's why I'll give you in a simple way these point defects. Mostly they'll ask you point defects. 5 defects are there. I'll explain these point defects in a simple way. Right? So one is vacancy. Vacancy means what? Missing of an atom. Missing of an atom. Okay? Missing of an atom like this. So this is a vacancy. This is. Second, Frankel defect. Frankel defect means what? Misplacing of an atom. Where? Misplacing of an atom to the where? Which position? Within the unit cell only, or within the structure only, it is moving to the interstitial position. So, misplacing of an atom from original to interstitial. See, listen, Frankel defects takes place in ionic crystals. Why? Difference in size. Like 1 plus, 1 minus, 1 plus, 1 minus, 1 plus, 1 minus, minus, plus. Minus is missing. Plus, minus, plus, plus, minus, plus, minus, plus, minus. It is moving from its original position to interstitial position. This is Frankel defect. Misplacing of an atom from its original position to the interstitial position is nothing but Frankel defect. These things only important. Next, third one. Schottky defect. Third one, Schottky defect. Okay, Schottky defect means what? Missing of pair of atoms. I said a couple are missing from the class. Right, couple is missing from the class. Couple means male and female both are missing in the class, right? So missing of plane of atoms. Missing of plane of atoms, like a cation, anion. Missing of plane of atoms, cation and anion. Missing of plane of atoms. So it is also takes place in the ionic structure, ionic crystals. Missing means they are moving into some other interstitial position. They are not completely out of the structure. Okay, na? They are present, but they are not in a complete out of the structure. Schottky defect maintains electrical neutrality, not Frenkel defect. Sai Krishna, not Frenkel defect. In Frenkel defect, there is only one atom is missing. Electrical neutrality is not present. Electrical imbalance. Imbalance is there. But in Schottky defect, electrical neutrality is there. Okay, remember these three defects. And one important thing I'll tell you, stoichiometric ratio. Especially in ionic crystals, stoichiometric ratio means what? Number of cations by number of anions. In one IS exam they asked number of cations by number of anions. The ratio must be perfect. For example, if you take sodium chloride, one sodium atom, one chlorine atom, they are making bond. Okay, if stoichiometric ratio is 1:1, what do you mean by 45%? 45%. There is no defects in the material. All the atoms are in the perfect order. Now, my question is, by creating Frenkel defect and Schottky defect, is it stoichiometric ratio is going to change or not? I am saying that it's not going to change because atoms are missing in the original place, but they are there in their interstitial spaces somewhere else. Within the structure only, within the big structure, take 1 meter cube of 1 mm cube of a block of salt. There are so many Schottky defects or Frenkel defect. Means atoms are misplacing. Means the atoms are not in the original position, but they are there in the present. So that we can say, even by creating a Frenkel defect or Schottky defect, the stoichiometric ratio may not change. Okay, na? Stoichiometric ratio means, otherwise leave it all this thing. Stoichiometric ratio means number of cations by number of anions. So even by creating Frenkel defects and Schottky defects, there is no change in stoichiometric ratio. Next, another one, substitutional defect. Substitutional defect means what? Adding impurity atom in place of host atom. Simple way I'm telling. And to form the substitutional defect, radius of foreign atom approximately same as radius of host material atom. Remember. The next is interstitial defect. Interstitial defect. And by doing this, what is interstitial defect? Adding impurities atoms at interstitial position. Adding impurity atoms at interstitial positions. Adding impurity atoms at interstitial positions. So for this, the main condition is the foreign atom size is very, very small in comparing with the host material atom. Definitions, basic definitions. You have to remember. Right? And line defects are there. Line defects or dislocations are there. Okay, it is nothing but a complete line of atoms are missing, or more than multiple atoms are missing. In a simple way, I'll explain line defects. Okay, based on the diagram, I'll explain. Remember the diagram. That's it. That is more than enough. Okay. Now listen carefully. The line of atoms are missing here. So this region, this defect region, this is a dislocation, and these two atoms are dislocated atoms. Now there are two line defects. One is edge dislocation. Second is screw dislocation. Edge and screw. If you apply the force, in case if the dislocated atoms are moving parallel to the force, that is edge dislocation. In case if the dislocated atoms are moving perpendicular to the force, that is screw dislocation. Remember the diagram. By applying force, if the dislocated atoms are moving parallel to that force, edge. If the dislocated atoms are moving perpendicular to the force, screw. And there is a Berger vector also. Berger or Burgers vector, Burgers vector. This Burgers vector is used to find the direction of magnitude for you. Direction. In edge dislocation, remember, in edge dislocation, this is the direction of the Burgers vector. So this Burgers vector is perpendicular to the line, dislocation line, okay, or parallel to the force. Burgers vector is parallel to the force in edge dislocation. And Burgers vector is perpendicular to the force in screw dislocation. Like that. Just remember these two. In edge dislocation, dislocated atoms are moving parallel. In screw dislocation, dislocated atoms are moving perpendicular. And Burgers vector is parallel to the force, perpendicular to the force. That's it. Remember these two. Rarely they'll ask you questions. And also, I gave grain and types of grain materials are grain boundary. So types of grains. There are two types: fine grain and coarse grain. Fine grain and coarse grain. Fine grain is having more grains, more small grains. A simple way I'll give you. Coarse grain is having less large size grains per unit area I'm taking, per unit volume or area. So fine grain, more boundaries, grain boundaries. Coarse grain, less grain boundaries or less boundaries. Fine grain, because of more boundaries, high strength, only at room temperature. Coarse grains, low strength, only at room temperature. Then, next is low strength. Fine grain materials are having low strength at high temperature. Coarse grained materials are having high strength at high temperature. Right? Magnetic properties, if you consider hard magnet, because of more boundaries, it is a soft magnet. And fine grains are having more defects now. More boundaries means more defects. So conductivity is low, resistivity is high. High resistivity. And here low resistivity. Remember these two. High resistivity and low resistivity. So these things are important. And one more formula I'll give you. You don't need to remember, just go to that. Hall-Pitch equation. This Hall-Pitch equation gives the relationship between strength of the material with grain size. So strength S is equal to S constant plus K by root 2D. Here S I'm taking it as a strength, or yield strength. I'm not using the word sigma because sigma is electrical conductivity, other people will confuse. You remember this. S is the strength, D is grain size. SC and comma K are constants. You don't need to consider constant. So for your exam point of view, maybe some questions they'll ask like, the strength of the material is inversely proportional to the grain size at room temperature. At room temperature, with increasing strength of the material, or with increasing the grain size of the grain, if it increases, the material lose its strength. That is Hall-Pitch equation. Remember that. Right? These are some of the important things related to mechanical, right? Okay. And also I'll give you some other things related to mechanical. That is alloys or solid solutions. If you take, okay, we discussed what is an alloy. Homogeneous mixture of two or more materials we are combining or mixing. Homogeneous mixing. That is an alloy. A solid solution, right? I explained it. But what is important here? Gibbs phase rule. For quick revision, what is Gibbs phase rule? F plus P is equal to C plus 2. Here F represents degree of freedom, means how many number of independent variables required. P is number of phases. C is number of components. Okay, now, but this is not applicable for the alloys. What is applicable? Modified Gibbs phase rule. Because for alloys, pressure is not changing. That way F plus P is equal to C plus 1. For your exam point of view, remember this formula. You don't need to remember F plus P is equal to C plus 1. That is mechanical people. For them, it is important. You remember this formula. Just remember the formula. In case in exam paper, if they are given number of phases, number of components, what is degree of freedom, substituting that. That is applicable for water system. In case if the water example is given, use that one. This is applicable for alloy systems. In case in exam paper, if the word they are given metal or alloy, use this equation. Gibbs phase rule. And next is there are two types of solid solutions. One is a substitutional solid solution. Second is an interstitial solid solution. Substitutional and interstitial. We know what is substitutional solid solution. The solute atom or foreign atom, if it is present at the solvent place, we can say substitutional solid solution. Right? And what is important for your exam? You know what is substitutional solid solution? Terms are conditions required to form substitutional solid solution. Right? Hume-Rothery rules. In 1 year, they ask this question. Hume-Rothery rules. In one IS exam, they ask this question. So what is this Hume-Rothery rules? Conditions required to form substitutional solid solution. Or sometimes they will give you simply conditions required to form the solid solution. For your exam point of view, just remember the names or conditions. You don't need to go in depth. Like crystal structure. So crystal structures of these two elements which are going to make an alloy must be same. You have to remember this. Crystal structure, first one. Second one is size factor. Second one. The difference in size means radius of a host material atom minus radius of foreign atom. Difference in size is less than or equal to 15% or 40%, like that. Difference in sizes must be less than 15%. Both. Next, third one, valence. Difference of the valence of both elements must be low. Difference of valence must be low. Then fourth one, electronegativity. If you consider, here also it is the chemical affinity to make a bond. So this difference in electronegativity is also low. Like that, you remember Hume-Rothery rules: crystal structure, size factor, valency, electronegativity. Just remember like this. Okay, these are the conditions required to form a substitutional solid solution. For interstitial solid solution, there is only one size. The size must be very, very low. Right? This is. Next is iron carbon diagram. Some important things I'll explain. Iron carbon diagram. Wait for some time. Iron carbon diagram. Okay, black color. Right. So next I'm going to discuss about iron cementite phase diagram. Important points I'll discuss. Okay, now no need to worry regarding that. Important points I'll discuss. See, x-axis represent percentage of carbon, right? Y-axis represent temperature. So remember, maximum solubility of carbon is 6.67. You can't add more than 6.67. That is one important thing. And based on carbon, there are two types of materials. One is steel, that is up to 2.1% of carbon. From 2.1 to 6.67, it is cast iron. Remember. Okay. And y-axis represent temperature, right? There are different types of allotropes of irons are there. Alpha iron, gamma iron, delta iron. Okay, right? So listen carefully. The alpha iron is from room temperature to this 19 degrees Celsius. What is the structure of this alpha iron? BCC. And this austenite is known as gamma iron. Austenite is known as gamma iron. From 19 degrees Celsius to 1400 degrees Celsius, the type of iron is known as gamma iron. That is FCC. From 19 degrees Celsius to 1400, that is gamma iron FCC. Again, from 1400 to 1535, that is again, it is known as delta iron. Delta iron. Okay. That delta iron crystal structure is again BCC. So remember carefully. Alpha iron BCC. Gamma iron, it is also known as austenite FCC. Delta iron, it is again BCC. Now, what is the Curie temperature of iron in this graph? They asked in the previous year IS. What is the Curie temperature? Where it is going to convert ferromagnetic iron material into paramagnetic iron material? 768 degrees Celsius. 768 degrees Celsius. This is 768. So I'll write these points also sometimes. The Curie temperature of iron is 768 degrees Celsius. Means above 768 degrees Celsius, it is para, and below 768 degrees Celsius, it is ferro. Above 768 it is para, below 768 it is ferro. Now listen carefully. Inside this, how many phases are there? 5 phases are there. Number of phases, how many? Number of phases, 5. One is liquid, no problem, liquid, there is no structure. Second is delta iron. This delta iron structure is what? BCC structure, and maximum percentage is soluble up to 0.09% of carbon. That is delta iron. Next, third one is gamma iron. It is also known as austenite. Okay, it is also known as austenite. The structure of austenite is FCC structure. The structure of austenite is FCC, and the percentage of carbon is up to 2.1. Out of all phases, this is the maximum one. So remember, in which type of iron more carbon is there means gamma iron, 2.1 it is there. Fourth one is alpha iron or ferrite. It is also known as ferrite, alpha iron or ferrite. Okay, and this alpha iron is having again BCC structure, and the percentage of carbon is up to 0.008%. Sorry, up to here this one, 0.025. 0.025% of carbon is there. This is important. Next, also equilibrium reactions. Equilibrium reactions also important. Equilibrium reactions also important. Some equilibrium reactions I'll give you. Okay, this one. Equilibrium reactions are basic definitions. They will ask you for your prelims point of view. For mechanical people, for them in depth, they'll ask you for your basic definitions of these equilibrium reactions. They'll ask you. One is eutectic reaction. What is eutectic reaction means? A liquid upon cooling transforms into two solid phases, solid 1 and solid 2. Cooling, or otherwise two different solids upon heating transforms into liquid. This is actually, this reaction is present here. I'm not explaining. This reaction is present here. Eutectic reaction. Okay, at 4.3% of carbon and 1100 degrees Celsius, this is going to be takes place. And less than this 4.3, the type of cast iron is hypoeutectic cast iron. And more than this 4.3, the type of cast iron is hypereutectic cast iron. Understand? There are two types of cast irons based on eutectic reaction. Eutectic reaction means what? One liquid upon cooling transforms into here gamma iron plus cementite. Okay, I forgot to give a cementite here. One more structure is there, cementite, fifth one, cementite. Its structure is orthorhombic structure. Its structure is orthorhombic structure, and the percentage of carbon is up to 6.67. Percentage of carbon is up to 6.67%. Right? Okay. Right. Now, this is the one reaction you have to remember for your exam. And the second reaction is eutectoid reaction. Second reaction is eutectoid reaction. What is this eutectoid reaction? One solid upon cooling transforms into two different solid phases. one solid upon cooling transforms into two different solid phases, or otherwise two different solid phases upon cooling heating transforms into a single solid phase. Okay. Now in this diagram, the point is this one, third point. This is eutectoid reaction. Above this eutectoid reaction, gamma iron is there, one solid. Upon cooling, this gamma iron transforms into alpha iron plus cementite. Now listen carefully. This is at 0.8 or 0.76, 0.8, you remember. So below this eutectoid point, it is a mixture of alpha iron and cementite is formed, that is known as perlite. This question asked in previous year IES or GS only. Okay, so I'll give you important point here. Perlite is an eutectoid mixture of alpha iron and cementite formed at 0.8% of carbon in iron. So remember, in perlite, the percentage of carbon is 0.8. So it is a mixture of both alpha iron and cementite. Like it is like this. Remember, in perlite, the cementite is present like this structure, surrounded by alpha iron. In perlite, cementite is present like this structure, surrounded by alpha iron. This is alpha iron, and this is cementite. In IS exam, previous year IS exam, from the perlite, what type of question they ask, which is a soft phase material in perlite and which is a hard phase material in perlite? Very simple. In perlite, two phases, alpha and cementite. In alpha iron, percentage of carbon is very low, so that it is soft. But cementite, percentage of carbon is very high, so it is hard. I said with increasing percentage of carbon, cementite formation increasing, hard phase is increasing. So remember, in perlite, alpha iron and cementite is present. Alpha iron and cementite is present. In the alpha iron is a soft phase material and cementite is a hard phase material. That is. So eutectoid reaction means one solid upon cooling transforms into two solids. Next, third reaction, that is peritectic reaction. What is peritectic reaction here? One liquid and one solid, upon cooling transforms into a different solid phase. One liquid and one solid upon cooling transforms into a different solid phase. Otherwise, this solid upon heating transforms into a liquid and solid. The second solid upon heating transforms into liquid and solid. That is nothing but peritectic reaction. The peritectic reaction is present here. Right? The peritectic reaction is present here. You no need to remember that. So listen carefully. In this iron cementite phase diagram, three reactions are there: eutectic, eutectoid, peritectic. All these three reactions are equilibrium reactions. So the degree of freedom of all these reactions are zero. You don't need to use the Gibbs phase rule formula. Okay, I'll write here only. Degree of freedom of peritectic reaction point is zero. Degree of freedom of eutectic point is zero, and degree of freedom of the eutectoid point is also zero. Okay, this is the information about iron cementite phase diagram. Remember, there is no peritectoid reaction in this phase diagram. Peritectoid reaction is there. I give that one. Leave it. Forget otherwise. Peritectoid reaction is not there. Only three reactions are there: eutectic, eutectoid, and peritectic. There is no peritectoid reaction is there. And actually, the lever rule is there. One lever rule method. Actually, the lever rule is important for mechanical. I'm not explaining much. But what I'll give you a basic meaning of the lever rule. The lever rule method is used to find the mass fractions of phases at a particular location. For example, listen carefully. At a particular point, like at this point, I want to know how much alpha iron is there, how much cementite is there. That mass fraction I can find by using lever rule method. Okay, now so basic definition of the lever rule I'm giving here. So lever rule method is used to find mass fractions of two phases. Okay, by using lever line. It is an isothermal line. What is lever line? Lever line is an isothermal line. How it is going to be? Because from this point, you draw left side and draw right side, calculate mass, find the mass concentrations, and then calculate that. That I'm not explaining numericals. So just remember the basic definition of the lever rule. Right. So this is the information about. This is the information about the lever rule, right? Peritectic, eutectic, and eutectoid. Now, different types of steels and cast irons are there. Okay, steels are low carbon steel, medium carbon steel, high carbon steel. But from the steels, they are not asking questions. But from the cast irons, they are asking questions. Types of cast irons. From the cast irons, they are asking questions. Okay, now every year one question, or alternating year one question, they are asking question. That's why I'll explain. There are 4 types of cast irons are there. 4 types of cast irons are there. I'll explain these cast irons based on the diagram. Now, first one is gray cast iron. Listen, carbon percentage is the same, more or less in all types of cast irons are same. No need to remember carbon percentage or silicon. What is important for GS? For mechanical people, they will read everything. But what is important for GS is in gray cast iron. Remember, in gray cast iron, graphite is present in flakes form. Remember, these black color one is graphite. The graphite is present in flakes form. Remember, this is. And because of the flakes wear and brittle in tension, strong in compression, excellent damping capacity. This you have to remember. Because of high damping capacity, this is used in machine beds. Very important. Or late machine bed. Why we are using this in late machine bed? Because it can able to absorb the vibrations. because of that. So what is important for your exam? In gray cast iron, graphite flakes are there. It is used as a machine. It is used to make a machine bed because it is having high damping capacity. That's it. High damping capacity. That is the first one. Then second one, nodular cast iron. This is the nodular cast iron. In nodular cast iron, graphite is present. This is a graphite. Okay, this is a graphite, spherical or nodal graphite. What is the shape of the graphite in nodular cast iron? Spherical or nodal? How can we get this nodular cast iron? Listen carefully. Magnesium and cerium. By adding magnesium and cerium to the gray cast iron, we will get nodular cast iron. By adding magnesium and cerium to the gray cast iron, we will get nodular cast iron. We will get nodular cast iron. Right? Magnesium and cerium. By adding magnesium and cerium, so we will get nodular cast iron. Right? And these cast irons are strong and much more ductile. Listen, this is also known as ductile cast iron because it's having some good ductility. Because in gray cast iron, graphite is present in the flakes form, so stress concentrations are more, so brittle. But here stress concentrations are less, sharp edges are less, so it won't break easily, it will deform. So that stress concentration points are very less, so that it is having good ductility. That we have to remember. Next, white cast iron. White cast iron. So listen carefully, it's a different one. Last year they asked this question, right? And in 2018 or 17 they asked about 2018 only they asked about this question, white cast iron. Listen carefully. Generally in cast iron, carbon is there. In gray cast iron, carbon is there in flakes form. In nodular cast iron, carbon is there in nodal form. But in white cast iron, no carbon, or most of the carbon is in the form of cementite. So no graphite. Remember like this. Right? So it is produced from the fast cooling. That is, remember, not a graphite. It is not having any graphite. Produced from the fast cooling. Very hard and brittle. Machinable is not possible. But this white cast iron is used to make a malleable cast iron. Means to make the malleable cast iron, we are using this white cast iron mostly. Understand? White cast iron, no graphite. Fast cooling, used to produce malleable cast iron. Remember that. Now, the last type of cast iron is malleable cast iron. So listen carefully. The malleable cast iron is produced from the white cast iron. Listen, malleable cast iron is produced from the white cast iron by applying annealing heat treatment process. Maybe here it is not given the word. Okay, now don't leave all these things. Just remember annealing process. Okay, malleable cast iron is produced from the white cast iron by applying annealing heat treatment. Annealing heat treatment is what, you know? Heat the white cast iron material up to certain very high temperature and cool the material with slow cooling rate. By cooling of that material with slow cooling rate, a rosette form of graphite, rosette form of graphite is formed. Remember, a rosette form of graphite is formed in the malleable cast iron. It is having good ductility, good strength, and good malleability or good ductility, right? So all these properties it is having. Understand? Malleable cast iron. So remember 4 cast iron for your exam point of view. That is important. So this is the information about alloys, phase diagrams, iron, carbon alloys, all these things. Okay, right? Now, next, another most weighted topic is material properties. Anonymous attendee, what is substitution, solid solution? Again and again, you're asking. I think you're new to this batch. Okay, without knowing proper material science subject, you can't understand. Now, you leave it. By doing substitutional means adding foreign atom in place of post material atom. That is. Okay, I will discuss last way that you are asking a different question point of arrest that is not required here basic somebody said. We'll discuss later that. Your civil, electrical, electronics people, so many other. It is first revision class. Sir, it is first revision class. Revision means only one class, not first, second. Okay, it is common for all branches, not only mechanical. Right. I don't know about this. Will this video uploaded or not? I don't accept it. Right. Okay, cast irons are over, steels are over. Now, next topic is material properties and testing. Basic questions they'll ask you, definitions they'll ask you. So, material properties and testing. Basic definitions they will ask you from this material properties and testing. Like one thing, you take true stress. Electrical electronics people, just remember the definitions. Concept is not required for you. Okay, it is true stress means what? Load by instantaneous area. Means corresponding to that load, what is the area of cross section of the material. And engineering stress means load by I don't know, Kavya, I don't know about that. You ask management, I don't know about that. Maybe you are 2021 or 2022 batch. Right, engineering stress means load by initial area. Engineering stress means load by initial area. True stress means load by instantaneous area. That means F amount of load, instantaneous area is AF. F amount of load, initial area is A. You just remember the basic definitions, that is more than enough. Next is ductility. Ductility means it is the ability of material that can be drawn into wires. Like, for example, this is the initial length of the specimen, Li. This is the initial diameter of the specimen, Di. Now I'm applying force, tensile force like that, F amount of force up to the failure point. It is deforming into wire, that is LF and DF. So ductility means it is the ability of material. It is the ability of material that can deform that can deform plastically. It is the ability of material that can deform plastically up to fracture or failure by applying tensile load. Okay, now it is the ability of material that can deform plastically up to the fracture by applying tensile load. How can we measure this? Percentage increase in length, percentage right? So ductility means it is the ability of material that can deform plastically up to fracture by applying tensile load. How can we measure that? Percentage increase in length, length is increasing, and cross-sectional area is decreasing. So percentage increase in length and percentage reduction in cross-sectional area. Remember these two. And malleability means what? Malleability means what? See, in ductility case, we are applying tensile load, but in the malleability case, if you apply the compressive load to the body, material length decreases, but diameter and cross-sectional area is going to increase. So that means we are applying compressive loads. That is okay. So malleability means it is the ability of material. It is the ability of material that can deform plastically in lateral direction. It can deform plastically in lateral direction by applying compressive loads. And measurement is also same. Here increasing length we written. So here we can say percentage decreasing length, length is decreasing. So it is measured by percentage decreasing length, percentage decreasing length, and percentage increasing cross-sectional area, percentage increasing cross-sectional area. So ductility and malleability, these are two, right? Percentage increasing length and percentage decreasing cross-sectional area, right? Now what is toughness? Toughness is the ability of material that can absorb energy or impact energy up to the failure point. Okay, ability of material that can absorb energy or impact energy up to failure point. It is the ability of material that can absorb energy or impact energy up to failure point, and it is measured by considering area of stress strain curve. Stress strain curve. Area of stress strain curve represent, for example, this is the area stress strain curve. So by calculating this area, we will get this area, that is stress into strain, that is Newton per meter square you are getting. But energy we are saying, that means we can write this Newton meter per meter cube. So energy per unit volume, that means toughness per unit volume, that is nothing but modulus of toughness. So remember, modulus of toughness and toughness same. Only difference is modulus of toughness means toughness per unit volume. It's an intrinsic property. This is toughness. Next is resilience. Resilience means what? Same concept. Here we took up to failure point, right? But in resilience, we are considering only up to elastic point. So ability of material that can absorb energy up to or within the elastic point. So it is the ability of material that can, it is the ability of material that can absorb, it is the ability of material that can absorb energy up to elastic limit. So how can we measure this resilience? It is the ability of material that can absorb energy up to elastic limit, right? How can we measure that one? Like, for example, this is the stress strain curve you take. So just to take up to the elastic limit only. This is elastic limit. Take the area. So listen carefully. Resilience is equal to half into stress into strain. Also sometimes in exam paper, if they ask in numericals, stress value they are given, strain value they are given. If they ask you what is resilience, triangle. It's a triangle. But this is resilience per unit volume. Now that means Newton per meter square it is. So we can say it's a modulus of resilience. You can say modulus of resilience. That is Newton per meter square. That is resilience by volume. So this area represents what? Modulus of resistance, not just resistance. But anyhow, if the given data is given, if they ask you resistance, take the area half into sigma into epsilon. That's it. Right. Now next is there are actually the toughness is measured by considering area of stress strain curve, that is for ductile material. Ductile only, because for ductile materials only we get more area. For brittle material you won't get more area. So for brittle material, toughness is measured by impact test. Impact test. This is used to measure the toughness of brittle materials. So there are two impact tests we have to remember. For example, one is simply support, cantilever beam, ISOR test, Charpy test. There are two impact test methods. One is ISOR test, second is Charpy test. Both are used to measure the toughness of brittle material. In ISOR test, the specimen is positioned like a cantilever beam. You just remember this one, that is more than enough. In Charpy test, the specimen is positioned like a simply supported beam. That's it. Next, hardness. Tell me, what is hardness? It is the ability of material that can resist scratch or indentation or penetration on the surface, right? So it is the ability of material that can resist scratch or indentation on the surface. Okay, now there are different hardness methods are there, like Brinell test. Brinell test formula, Brinell hardness number formula. You don't need to remember. Just go to that. 2b by root of pi d into d minus root of capital C, not root, pi d into d minus root of capital D square minus small d square. No need to remember. Just go to. Otherwise, if you want low hard materials, for low hard materials you are using. Then second is Vickers test. This Vickers test is Vickers hardness number 1.854 p by diagonal square. It is used for very high hard materials. And the third one is Rockwell test. This Rockwell test is used for all materials. Here, depth of penetration. Rockwell test, we are measuring depth of penetration is proportional to 1 by hardness. If hardness is more, depth of penetration is less. If hardness is less, depth of penetration is more. Understand? If the hardness is more, depth of penetration is less. If the hardness is less, depth of penetration is more. These are different material properties, basics I covered, definitions and basics. These 2 mark questions, general studies, basics only they will ask you. Right. Okay. Next, more weightage topic is polymers. Okay. More weightage topic is polymer. Listen. Here, listen carefully. This is, I think, some 17 pages are there. Go through the 17 pages. Definitely 1 or 2 questions I'll give you guarantee. 1 or 2 questions. Definitely 1 or 2 questions they'll ask you from these 17 pages. I'll give you what is important also here. What is important also I'll give you here. No need to worry. What is important also I'll give you. So this polymerization not required, monomers not required. Okay. And listen carefully. Classification of polymers based on the source of origin. There is a natural polymers, synthetic polymers. These are there. If you want, you just go through this table. Otherwise, not required. Semi-synthetic polymers not required. But this is important. Remember, classification of polymers based on structure. This is very, very important. There are 3 types are there: linear chain polymer, branched chain polymer, and cross-linked polymer. These 3 you have to remember. Listen, in linear chain polymer, there is only one chain. See the diagram here. There is only one chain. Okay, and between these chains, there is a weak van der Waals bonds present. Right, and properties of these examples and properties also given. High density polythene, nylon, polyester all comes under linear polymers. And the density is more for the linear polymer chain compared to the branched chain. What is branched chain? In a simple way, there is a one main branch of the polymer, and the sub branches are there with the different dimensions of these polymers. Okay, so that gaps are more, so it is not closely packed. So low density is having low density, low tensile properties, low tensile strength, as well as low melting point, right, and low boiling point. But examples of these are low density polythene. Polythene covers are there in shops. Low density polythene covers comes under branched polymer. Starch, glycogen comes under this category. So linear and branch. Then third one is cross-linked. In cross-linked chain, the diagram is like this. There are so many linear chains, and perpendicular to these linear chains also covalent bonds are present, right? So highly complex one this is, and strength is more brittle, hard, right? Bakelite, glyptol, melamine, formaldehyde comes under this category. So you have to remember these 3: linear, branched, and cross-linked. Next step. Listen carefully. And based on the polymerization technique also, there are 2 types of polymers. One is addition polymerization technique, second is condensation polymerization technique. Okay, I'll explain these things also here. Here, within addition polymerization, homopolymer means single unit, number of times it is multiplied. Ethene, polythene. Vinyl chloride plus vinyl chloride, polyvinyl chloride. Homopolymer, single monomer, single type of monomer if it is having, that is comes under homopolymer. I'll upload this PDF, don't worry. I'll upload this NCERT PDF. I'll upload this one. Compulsory 1 question from this PDF, 17 pages. Very easy one. And also I'm stressing where you have to focus in from this PDF. Homopolymer basic definition and copolymer also basic definition. Copolymer means not only more than one monomer if it is having in the chain. More than one monomer if it is having in the chain, then it is a copolymer. More than one monomer, copolymer. Only one monomer, homopolymer. Right? This is the, and one more important thing, in addition polymerization, there is no byproduct generated. By combining 2 monomers, by adding 2 monomers, right, by using some chemical reaction, there is no byproduct generation in this. But in the condensation polymerization technique, there is a byproduct generated, like water, alcohol, hydrogen, right? This is a condensation polymerization. Now you need to remember these things, and you have to remember thermoplastics and thermosettings. That is also important. So thermoplastics are having linear polymers or branched polymers, and between these polymers, weak van der Waals bonds are there, so that they become very weak upon heating temperature, increasing the temperature, heating of the material, right? So upon cooling again, they become harder. Thermoplastics, polythene, polystyrene, right, PVC pipe, all these comes under thermoplastics. Remember, thermoplastics are reusable. Why it is reusable? Because these are having weak van der Waals bonds. In case we consider thermosetting, the thermosetting polymers are not having the van der Waals bonds. They are having cross-linked chains, so that highly complex. Upon heating, they won't become soft. They become more and more hard. Like we take the best example of switchboard. Take the switchboard. It is made up of bakelite. That is thermosetting. If you heat that switchboard material, it won't become softer. After some certain high temperature, it is going to burn. Right? That is comes under thermosetting plastics. And types of polymerization here. The chain growth polymer, all these things not required. But one important thing, how the polymerization takes place. There are 3 steps to form the polymer. One is initiation, chain initiation. You have to remember. Then chain propagation, then chain termination. Remember these 3 words. You need to remember the chemical reactions. Polymerization process is done in 3 steps. Chain initiation, chain propagation, chain termination. These three words, they will ask you in the objective type question, which are the given below, are orderly mentioned the given below steps in the polymerization technique: initiation, propagation, termination. Right? And remaining things you don't need to remember. These things you don't need to remember for your exam point of view. Not required. Not required. Not required. These things are not required. Now here it is important. Now each type of polymer they explained. Polythene. Okay. One is low density polythene. You don't need to remember this reaction. Okay. Now, but what you have to remember, tough, flexible, transparent, chemical inert, poor conductor. Where it is used, what are the properties? High density polythene. Where it is used, what are the properties? Toys, bottles, housewares, electrical insulation, high density polythene. Polystyrene. Polystyrene where it is used, PVC pipe where it is used, polypropylene where it is used. These things you have to remember. Basic applications, nylon 6 where it is used, right? Reactions you don't need to remember. Reactions you don't need to remember. Just to go through the applications and properties. Applications and properties. Listen, this is important. Polymethyl methacrylate, right? Where it is used, where it is used. Acrylic, plexiglass, glass purpose for making of glasses. We are using this one. Glyptol, it is paints, manufacturing of paints. We are using this glyptol. Terylene, where it is used. Terylene is given or not? Catalyst mixture of zinc acetate. It is formation of terylene is given. Application is not given. No need to worry. Given properties. Manufacture of variety of cloths like terrycoat, terrywool, terrysilk. So terylene is used to make called cloths, tapes, conveyor belts, aprons, etc. Now this is important for your exam. That is biopolymers or biodegradable polymers. You have to remember the names. See, listen carefully. Biodegradable polymer. One is aliphatic polyester. Aliphatic polyester is one of the biodegradable polymer. Aliphatic polyester. You have to remember the name. You have to remember the name. Aliphatic polyester. And nylon 2, nylon 2 and nylon 6. These are also biodegradable polymer. Right? So you just go through these things. Super glue is a polymer of methyl alkocyanoacrylate and is obtained by ionic polymerization of monomer. Not required. Silk is a thread-like natural polymer which is obtained from cocoons of silkworm, which is a natural polymer. Right? Like that. Thiocol is another variety of synthetic rubber which is a copolymer of ethylene chloride and sodium tetrasulfide. Like that. Basic things you just go through one time. That is more than enough. From this one night. Okay. From this one you just go through one time. I'll upload this note. Don't worry. And one more. Okay. One more important thing I'll tell you here. Add image, polymer structure. In one IS exam, listen carefully. In one IS exam, they asked basic structure of the monomer. Basic structure like polypropylene. You have to remember this monomer structure. Basic propylene structure. Polystyrene. You have to remember the structure. Polyvinyl chloride. You have to remember the structure. So this is also you just go through this one. Basic structure. Bakelite. What is the monomer? Phenol, formaldehyde. Glyptol. What is the monomer? Ethylene glycol. These things you have to remember for your exam. Okay, just before going to the exam, please go through that. Right? This is the information about polymers. Right. Next is related to the electrical properties, electrical and magnetic properties. Like if you consider electrical conductors. Okay, increase the electrical. Monomer name and structure. You have to remember monomer name and structure. Structure, chemical formula is there. Basic chemical formula, basic unit. You have to remember. Right. Electrical properties. If you consider, and based on free electron theory, you have to remember that electrical conductivity is Ne mu. N is number of electrons. E is 9.1 into 10 power. Sorry, 9.1 is mass 1.6. 1.6 into 10 power minus 19 coulomb charge. It's electron charge. Mu is the mobility of an electron. You have to remember this formula based from the basic formula. Sometimes they'll ask you questions. From the basic formula, they'll ask you questions sometimes. Right? And energy band gap theory. Energy band gap theory. From this, there are three materials are there based on energy band gap theory. Conductors. In conductors, energy band gap is 0. Conduction band and valence band overlapping with each other. This is the conduction band, this is the valence band overlapping with each other. But listen carefully. In conductors, with increasing temperature, lattice vibrations are increased. Increasing temperature, lattice vibrations are increased, so that resistivity increased and conductivity decreased. So with increasing temperature, resistivity increased, so that positive temperature coefficient of resistance or resistivity materials. Remember, conductors are also known as positive temperature coefficient of resistance materials. Why? With increasing temperature, due to the lattice vibration, resistivity increased. Examples for this is all metals. All metals comes under this category. Then second one, semiconductors. Semiconductors. In semiconductors, energy band gap is very less. That is 1 electron volt to 2 electron volt. Very small, minute gap is there between the conduction band and valence band. Right? And you have to remember that in semiconductors, at absolute 0 Kelvin temperature, due to small energy band gap, the electrons can't move into the conduction band. So it acts as an insulator. Semiconductor acts as an insulator. And with increasing temperature, mobility of an electron increased. Right? Compared to the collision, the speed is going to increase. So conductivity is increased and resistivity is decreased. So with increasing temperature, resistivity is decreasing. That's why negative temperature coefficient of resistance materials. negative temperature coefficient of resistance materials. Examples like silicon and germanium. Third one is insulator. In insulator, energy band gap is more than 5 electron volt. Very large energy band gap it is there, so that the electrons can't jump into the conduction band from the valence band, so that it acts as an insulator. That's it. This is free electron theory. And next is Franch-Lorentz law. Franch-Lorentz law. The Franch-Lorentz law gives the relationship between electrical conductivity and thermal conductivity of material at a particular temperature. What is that Franch-Lorentz law? K by sigma is proportional to T. Rohini, why are you raising hand? What is the problem? Superconductor. I'll explain, Rohini. Wait. Right? K by sigma is proportional to T. K is thermal conductivity. K is thermal conductivity by electrical conductivity is equal to Lorentz constant into T. L is the Lorentz constant. Remember, for your prelims point of view, basic definition you have to remember. For your prelims point of view, basic definition you have to remember. Ratio of thermal conductivity to the electrical conductivity directly proportional to temperature. It is related to metals only, conductors only, not for semiconductors. Right. Next is factors affecting. Rahul Sharma, we will discuss later. Doubts, okay? Rahul Sharma, we will discuss later. Creep and fatigue is mostly related to mechanical. If you want, Rahul Sharma, you're mechanical, for you no need to explain. Other people, if you want to go through that, I can't explain here within 3 hours. Go through that. Now, factors affecting resistivity of the metal. Factors affecting resistivity of metal. Now, there are different factors. One is defects. Now, listen, with increasing defects, collision of electrons increases. And due to that, collision of electrons increases, and due to that, resistivity increases. Okay, with increasing defects, collision of electrons increases, and due to that, resistivity increases. Second, with increasing temperature also, collision of electrons increases, and due to that, resistivity increases, conductivity decreases. RT2 is equal to RT1 into 1 plus alpha into T2 minus T1. You have to remember this equation. Very, very important. In one IS exam they asked. Means resistance at T2 temperature is equal to resistance at T1 temperature into 1 plus alpha. Coefficient of thermal expansion. Coefficient of thermal expansion. This is okay. Coefficient of thermal expansion. Temperature defects. Next, third is alloying or solid solution. Alloying or solid solution. By adding alloys, by adding impurities, resistivity increased. Resistivity increased due to disrupt in structure. Otherwise, due to disturbance in structure only. Disrupt in structure or expansion and contraction takes place between the atoms, so that there is a collision of electrons, so that it is going to be takes place. Next, fourth one is cold working or plastic deformation or hard drawn. All are same. Cold working, plastic deformation or hard drawn. All are same. Means in simple way I tell you, at room temperature, take the wire and heat with hammer. That is nothing but cold working. At room temperature, we are deforming the body. By doing this, in a material, defects are generated. Due to this, defects are generated, so that resistivity is going to increase. Okay. These are the 4 factors you have to remember. Listen: defects, temperature, alloy, plastic deformation, or cold working. Now listen, residual resistivity. There are 2 types of resistivities. One is residual resistivity is the resistivity due to defects plus resistivity due to alloying plus resistivity due to cold working. Why I'm giving this is because which are the given below factors influence the residual resistivity, or which are the given below parameters are related to residual resistivity: defects, alloys, cold working. There are 2 types of resistivities: temperature resistivity, that is due to temperature; residual resistivity, that is due to defects, alloy, cold working. Remember like that. And one applications also I'll add electrical materials application. This is so before going to the exam, please go through this. Now listen, heating element of filament lamp. Heating element of filament lamp is a tungsten. Resistors for precision instrument, manganese, very, very important. That is manganese and iron, nickel, like that. Manganese. Resistors for precision instrument. To measure the measurement equipment purpose, resistor manganese value. Resistor for loading rheostats. Rheostats purpose constant. Copper nickel is constant. It is asked in ISRO. This is also known as Eureka. Asked in ISRO for electrical people. Constantan is also known as Eureka, and also mechanical people. This is used in thermocouples. In thermocouple, to measure the temperature, we are using this constant material. And resistors for electrical headers, electric heater, in a simple way, electric heater, nichrome. Insulator for 33 kilovolts, transmission line insulator, porcelain we are using. Stator and induction motor, steel laminates, silicon steel laminates. No need to remember remaining things. Just remember manganese, constantan, nichrome, porcelain. Tungsten, manganese, constantan, nichrome, porcelain. Remember. Right. These are different electrical conductors. Now, if you consider semiconductors, basics they'll ask you. Okay, there are intrinsic semiconductor. Intrinsic semiconductor means pure form of semiconductor. Like example, you can take directly silicon, germanium. Silicon and germanium directly act as a intrinsic semiconductor. For intrinsic semiconductor, due to the electrons and holes, both number of electrons is equal to number of holes. Okay, number of electrons is equal to number of holes. So that due to the electrons and holes, both conduction takes place. So that sigma is equal to Ne. Sorry, sigma is equal to n electron E into mu electron plus n hole into E into mu hole. You have to remember this formula. Right? Okay. For intrinsic semiconductor. And what about Fermi level? For intrinsic semiconductor, the energy band gap in between, if you take this is the conduction band, this is the valence band, and the Fermi level is located exactly at the middle. This is Fermi level. Exactly at the middle, you will get. This is intrinsic semiconductor. Next, the second is extrinsic semiconductors are two types. Extrinsic semiconductors, two types. Right? One is P-type. P-type extrinsic semiconductor examples are what? Third group element plus fourth group element, like boron, aluminum, gallium, indium. These elements plus silicon and germanium. Any combination you can take. Right? Number of electrons are greater than number of holes. So that electrical conductor, P-type now. P-type means number of holes are greater than number of electrons. Number of holes are greater than number of electrons. So sigma P-type is equal to n number of electrons into E into mu, sorry, NH into E into UH. NH, number of holes, mobility of hole. And Fermi level, where it is located? This thing is important. Fermi level, where it is located, tell me. Conduction band, valence band. So Fermi level, where it is located? Very nearer to the valence band. Correct now? Is it correct or not? Fermi level, it is very near to the valence band because there is one hole is present, extra hole is present. Yeah. Very near to the valence band. Then next is N-type semiconductor. Is it near the valence band or conduction band? I forgot. I'll give you later by there. First slide. N-type semiconductor. So N-type semiconductor is formed by adding fifth group elements to the silicon and germanium. Fifth group elements are nitrogen, phosphorus, arsenic, and antimony. By adding these elements to the silicon and germanium, we will get N-type. So the number of electrons are much greater than the number of holes. So electrical conductivity of N-type is equal to number of electrons into electron charge into mobility of electron. Okay, now, and the Fermi level is located, where it is located? Very nearer to the conduction band. This is conduction band. This is valence band. I have a doubt here. Tell me, electrical people, it's correct now. Electrical people, very nearer to the conduction band. This is Fermi level. Correct. N-type semiconductor. P-type, N-type, intrinsic formulas. We just go to that. Then compound semiconductor means what? Compound semiconductor. Compound semiconductor means by combination of more than one element. Like compound semiconductor formed by compounding third group elements with the fifth group element. Compounds of third group, fifth group elements, crystal structure is zinc blend we discussed now. Like third group elements are boron, aluminum, gallium, indium. Fifth group elements are nitrogen, phosphorus, arsenic, antimony. Like within the compound semiconductor, one is binary. In the binary, one element is from third group, one element is from fifth group. And in tertiary. In tertiary, one element is from two elements are from the third group, one element from the fifth group. Otherwise, two elements from the fifth group, one element from the third group. This is the compound semiconductor. P-type, N-type compound. That is okay. Next is magnetic materials. Magnetic materials. Okay. From the magnetic materials, basic fundamentals, if you talk about basic fundamentals, basic terminology, susceptibility, that is magnetization by applied magnetic field, that is M by H. And relative permeability, that is permeability mu by permeability of free space, that is mu by mu naught. Then relationship between these two, mu r is equal to 1 plus susceptibility, remember. This is important. Mu r is equal to 1 plus susceptibility, you have to remember. Now, and one more formula, magnetic field is generated H, that is number of turns into current by length of the coil. N is number of turns. Basic question, numerical, they'll ask you. I is current and L is length of the coil. L is length of coil. Permeability mu is equal to B by H. You can remember this also. And there are 5 types of magnetic materials are there. There are 5 types of magnetic materials are there. 5 types of magnetic materials are there. I forget to take these types of magnetic materials. This one I take. Not. Now listen, there are 5 types of magnetic materials are there. Remember, from this table also there may be a chance to ask a question. Diamagnetic material susceptibility is positive and negative. You have to remember negative is important. In the diamagnetic material, without any magnetic field, there is no dipoles, no magnetic dipoles without field. By applying field, minor dipoles in the opposite direction. That's why negative you got. Remember, diamagnetic material, negative magnetic susceptibility. It is not having any permanent dipoles. By just applying some field, it is going to generate dipoles, but they are in the opposite direction. That's why negative. Paramagnetic material, magnetic susceptibility is positive and very small. It is not very high. Most of the dipoles are randomly it is present. No dipoles, randomly orientation of the dipoles. Okay, na? So because of that, very small magnetic material, and it follows Curie's law. Remember, paramagnetic material follows Curie's law. Depends on temperature, follows Curie's law. So susceptibility is equal to C by T. Remember, susceptibility is equal to C by T. Paramagnetic material follows Curie's law. Next is ferromagnetic material. The ferromagnetic materials are having large and positive magnetic susceptibility and relative permeability very high. Because of that, it is used in applications also. This is not minus. This is approximately. Okay, now this is approximate word. Approximately 1 lakh susceptibility like that. All the dipoles are aligned in the same direction. So very large intensity of magnetization, and it follows Curie's law. Curie's law. Okay, susceptibility is equal to C by T minus theta. Just remember the law, Curie's law. And also above Curie temperature. This is ferromagnetic material above Curie temperature. It convert into para. Ferromagnetic material above Curie temperature convert into para. Next, antiferromagnetic material. This antiferromagnetic material is also positive and small. Anti-parallel dipoles with equal magnitudes. Here it is given anti-parallel dipoles with equal magnitude, small intensity of magnetization, and follows Neal's law. Neal's law, that is susceptibility is equal to C by T minus theta, T plus theta. This is T plus theta, that is T minus theta. And here above Neal's temperature, it convert into para. Remember, above Neal's temperature, antiferro, above Neal's temperature, convert into para. Antiferro, above Neal's temperature, convert into para. And finally, ferrimagnetic material. Ferrimagnetic material is also known as ferrites. Remember, ferrimagnetic material is also known as ferrites, and it is also having very large intensity of magnetization, right? And it also depends on temperature, but there is no particular law. Here susceptibility is equal to C by T plus or minus theta, you can take. And right, it is also above Curie temperature, it transforms into para. They may not ask you, but they will ask you temperature related concept questions, para, ferro, and antiferro. Para, ferro, and antiferro. You have to remember these things. And next, one more important thing here. Hard and soft magnetic material. I'll give you. Wait, that is also asked in one IS exam. I'll give you the properties of hard. Theta is the temperature. Theta is temperature. Okay. Theta is temperature. So hard and soft magnetic material also I'll give you. Hard and soft magnetic. Complete information is there. Right. Now see here, hard and soft magnetic material, very simple. Listen carefully. Maybe this diagram here it is given wrong. Here it is given wrong. You can take up to here only. Okay, you can take up to here remaining properties here. So soft magnetic materials easily magnetized and easily demagnetized, and also high saturation magnetization. But if you compare with this, we can say comparison. If you take the comparison low only, otherwise it is also having good magnetic properties, low coercivity, high permeability, low magnetocrystalline anisotropy, low magnetostriction, low core loss, high resistivity. Right, and hard magnetic materials difficult to magnetize and demagnetize. Permanent magnets applications here, inductors and transformer cores, recording head. Here permanent magnets and recording media. Right, high saturation magnetization. This is not low. This is high coercivity present here in hard magnet. High coercivity and also high retentivity. High retentivity present. Right, you just go through this table, this concept. High coercivity, high retentivity, low coercivity, low retentivity, low saturation magnetization. Right? Hysteresis losses, which is having low hysteresis losses. That is hysteresis losses is nothing but energy product. Hysteresis losses are high. Hysteresis losses are low. Like that, remember. Okay. So this is the information about magnetic materials. Okay. This is the information about magnetic material. Next is superconductors. I'll give you the properties, basic properties of the superconductor. Superconductors. For your exam point of view, basic properties only important. Superconductor means what? Perfect conductor. Perfect conductor of zero resistivity and infinite conductivity at below critical temperature, critical transition temperature. Below critical transition temperature. Superconductor is a perfect diamagnetic material. Perfect diamagnetic material with magnetic susceptibility. Magnetic susceptibility is -1. Remember, this is very, very important. Magnetic susceptibility is -1. Then third, Meissner effect. Meissner effect is also present in the superconductor. That is expulsion of magnetic flux lines. Expulsion of magnetic flux lines by superconductor. Then you have to remember one formula. Magnetic field at T temperature is equal to magnetic field at 0 Kelvin temperature into 1 minus T by T critical transition temperature whole square. Okay, just remember this one. Parabolic curve will get. Otherwise, just cross check that class notes. Otherwise, like class notes. Okay. Then another property of the superconductor is superconductivity of material is destroyed by. How can we destroy the superconductivity of material? How can we destroy the superconductivity of material? One is increasing temperature. One is increasing temperature. Second is increasing magnetic field. Increasing magnetic field. Third, increasing current. Increasing current. By using these three parameters, we can increase. Isotopic effect means the critical transition temperature of a superconductor is inversely proportional to mass of isotope. Mass of isotope. With increasing the mass of isotope, transition temperature is decreased. TC means critical transition temperature. Critical transition temperature. With increasing mass of isotope, the critical transition temperature is decreases. And also in superconductor, entropy increases with increasing temperature. Just remember these points. That is more than enough from the superconductor applications. You don't need to remember properties and definition. That is important from the superconductor. Right. Next is ceramics. From the ceramics, you have to remember one table. With increasing temperature, entropy always increases. Remember, with increasing temperature, at absolute 0 Kelvin temperature, it is low or 0. But with increasing temperature, entropy always increases. 2 and 3 same. Okay, no problem. No, sorry. And miss radius ratio rules. And this is also very, very important for your exam. For your exam from the ceramics. Every year, 2 years, they ask a question, 2 questions. One is from these two only. See, listen. They asked minimum radius ratio of a ceramic material in which one atom surrounded by 3 atoms. That means a triangular plane. One atom surrounded by 3 atoms. Coordination number is 3. One atom surrounded by 3 atoms. Coordination number 3. Minimum radius ratio they asked. Minimum radius ratio. Radius ratio means radius of cation by radius of anion. Minimum. That is equal to this one, 0.155. In case if tetrahedral structure means one atom surrounded by, there are 4 atoms like this. One atom surrounded by 4 atoms, that is a tetrahedral. Coordination number is 4. Then minimum radius ratio for this is 0.225. In case for octahedral, remember, octahedral means don't think that there are 8 atoms surrounded by 1. That is not correct. Octahedral means one atom surrounded by only 6. Coordination number is 6 is given here. So minimum radius ratio for octahedral is 0.414. For cubic structure means BCC means one atom surrounded by 8. That is cubic structure minimum radius ratio is 0.732. So you have to remember here 0.155, 0.225, 0.414, 0.732, 0.155 for coordination number 3, 0.225 coordination number 4, 0.414 coordination number 6, 0.732 coordination number is 8. Triangle, one atom surrounded by 3. Tetragonal, one atom surrounded by 4. Octahedral, one atom surrounded by 6. Cubic, one atom surrounded by 8. If you remember this, that is more than enough. If you remember this, that is more than enough from the ceramics. Okay, right? So this is the information. These are the different things related to the basics of material science. Dielectrics also there, but from the dielectrics rarely they are not asking questions. Dielectric materials they are not asking. But anyhow, I'll give you different dielectric materials. One is piezoelectric material. So piezoelectric material is what? It converts mechanical energy into electrical energy or electrical energy into mechanical energy. Quartz is the example for piezo. Then pyroelectric material is what? Pyroelectric material is what? With increasing temperature of a material, polarization takes place. With increasing temperature of material, polarization takes place. That is pyro. Then ferroelectric material. Ferroelectric is important. By increasing the voltage, by increasing the applied field or voltage, polarization increases. So these ferroelectric materials are used in capacitors. Very, very important. The ferroelectric is material same as ferromagnetic material. It depends on temperature also. Above Curie temperature, it converts into paraelectric. Okay. Above Curie temperature, it converts into paraelectric. And there are 3 types of polarization techniques. Basically, important 3 types of polarization techniques. One is elemental polarization or electronic or elemental polarization. Elemental or electronic polarization means what? In elemental or electronic polarization, okay, in elemental or electronic polarization, there is a separation of nucleus and electron. By separation of nucleus and electron with some distance. Then second is ionic polarization. Ionic polarization means what? Separation of cation and anion with some distance. Cation and anion. This ionic polarization takes place like alkali coin, sodium chloride, potassium chloride, hydrogen chloride, hydrogen fluoride, sodium bromide, like that. This is going to take place in all elements, even in inert gases. Remember, there is no magnetization or magnetic power in inert gases. There is no magnetization or magnetic power in inert gases. But this is also takes place in the inert gases, like elemental polarization, like helium, neon, argon, krypton, xenon, radon. In all elements, it is going to be takes place. And third one, finally, orientational polarization. Orientational polarization takes place in Asymmetric arrangement of atoms material. Asymmetric means non-centrosymmetric materials. Like you can take example of water. Okay, in water, 2 hydrogen atoms, 1 oxygen atom is there. This is hydrogen ion, this is hydrogen ion, this is O2 minus oxygen ion. The centers are not coinciding here because of this asymmetric. So there is a separation of cation and anion. There is separation of positive charge and negative charge. So because of orientation of the atoms, the polarization is generated. Polarization generated is nothing but charge is stored in the material. So orientation and polarization is mostly generated in asymmetric materials. Permanent dipole it is having. Permanent dipole it is having. In symmetric arrangement of material like CH4, CCl4, atoms are in perfect order. Cations and anions. So centrosymmetric arrangement is there. So there is no permanent dipole. So orientation won't take place. Polarization won't take place. Here polarization is equal to n into dm square, dipole moment square into mu naught by 3 kT into E. Here what I am saying from this, polarization is proportional to 1 by temperature, especially for orientational polarization. Means with increasing temperature, the polarization, that means charge storage capacity is decreased. In this case, polarization P is proportional to radius of the atom, RQ. If the size of the atom is increases, more separation distance increases, so polarization increases. So in elemental or electronic polarization is proportional to RQ. For ionic polarization, you don't need to remember, right? So this is the complete information about material science. I hope I explained most of the things I covered in a short period of time. I'll upload this PDF also. You just go through that, you should revisit it. And also wherever you got doubt, you just go through the live class notes. That is more than enough, right? Okay. And now we will discuss the doubts related to mechanical energy and electrical energy. Piezoelectric material convert mechanical energy into electrical and electrical energy into mechanical. Okay. Next. What are the doubts? Nanomaterial, no nanomaterial. See, the syllabus is basics of material science. Syllabus is not given in IS. Basics of material science. Basics. Nanomaterial is not basic. Nano is an advanced. For technical people, electrical, electronics, and mechanical. For technical people, nanomaterial is there. That's a different case. Okay. Next. Metamaterial also not required. Metamaterial you need to remember. No need to. Metamaterial is nothing but a composite material. Not required. It's advanced material. I don't know about this video. I don't know. Non-ferrous materials and alloys, PPT is there. I'll upload that PPT. Otherwise, you don't have time to read so many things. Most of the things are by hearting. Like if you take aluminum alloys, lead alloys, you have to by heart. Where is the time to by heart all these things? So that's why I'm not explaining. Theta is also temperature. That is a different temperature. Anonymous attendee, which branch? Theta is also temperature. T is also temperature. That's a different temperature. So heat treatment methods asked in paper one GS. Yes, heat treatment methods asked in GS, but it is not a simple one. Heat treatment is a complete core mechanical topic. Complete core. Other people can't understand. That's why for mechanical I explain. But other people it is. See what I'm saying. Out of 15, 16 questions from the material science, you can hardly able to get some 10, 11 questions. You can't get all questions. Such a complex subject is this. Even getting 10 questions from these notes is very good. Okay, from nowhere else you will get 100 questions from the same class or same textbook or notebook. Okay, you have to prepare. Out of the 15, 14 questions, you will get some 8 questions, 10 questions. That's it. Okay. Fermi level is an highest electron energy level. Hall effect is there. Hall effect I forgot to explain. Listen carefully. Hall effect. It is also a core subject, but I'll explain. Listen. Hall effect is used to find the type of a semiconductor. Hall effect is used to find the type of semiconductor. So in a simple way, I'll tell you. For example, take a particular cubic material. You just consider this a material. I'm sending electric field in this direction. Okay, I'm sending electric field in this direction, x direction. Once if I send the magnetic field, if I apply the magnetic field to the same material in the perpendicular direction, electrons instead of moving in this direction, they are deflected like this vertically. Understand? Electric field in this direction, magnetic field in this direction. Then due to that applied magnetic field, electrons are deflected in the perpendicular direction. Based on Fleming left-hand rule, you remember. Electric field, magnetic field. Because of applied magnetic field, electrons are deflected perpendicular to that. Then by connecting electric terminals to that electron flow, you will get the Hall voltage. If the Hall voltage is 0, it is intrinsic semiconductor. If the Hall voltage is negative, that is n-type semiconductor. If the Hall voltage is positive, that is p-type semiconductor. So, principle I write here. Hall voltage is generated perpendicular to the applied magnetic field and perpendicular to the applied electric field and transverse. Transverse is also perpendicular. Transverse magnetic field based on Fleming left-hand rule. Based on Fleming left-hand rule. Now see here under Hall voltage VH 0 intrinsic semiconductor. Hall voltage is positive p-type semiconductor. Hall voltage is negative n-type. And this Hall voltage experiment, this Hall experiment is used to determine type of semiconductor, number of electrons per meter cube, mobility of electron, electron charge, electrical conductivity, etc. This is Hall effect related to semiconductors. Ferroelectric material and ferromagnetic material do these both show same characteristic, that is high reactivity and high reactivity and low coercivity. Yes. First of all, ferroelectric, it's not ferroelectric. Perimagnet and ferromagnet both are having good reactivity and low coercivity. But what is the difference? Ferroelectric materials are good conductors. So eddy current classes are generated. Current flow is there, so eddy current class is there. But ferrimagnets are ceramics, spinal structure ceramic, so that they do not generate eddy current classes. RH value of P type and N type. RH value is, I am not explaining here, Hall voltage coefficient for P type and N type, both are negative only. And I must attend RH value is negative for both. Conductors, Hall voltage is negative or positive? For conductors, tell me, imagine, for conductors, Hall voltage, is it positive or negative? There is more electron flow, is there? More electron flow, more Hall voltage is generated more. Is it is negative or positive? Due to the electron flow that is negative. N type electron flow negative. Conductors electron flow negative, like that. D orbital concept, one more magneton, it is there, but we can't explain everything, right? I'll upload the video. Rahul Sharma, if you want to calculate linear density, first of all, you should draw the structure. Like, for example, Rahul Sharma, I'll give you reason. Rahul Sharma and Manish, I think, so two people they asked. For example, if they asked a simple cubic structure, 100 direction, what is the density? First, you have to draw the structure of simple cubic structure, locate the atoms of simple cubic structure, and locate origin x-axis, okay, y-axis and z-axis. Then draw the direction. This is 100 direction. Count number of atoms are there, how many, and what is the length of the direction. Like that, you have to measure. That is not, you can't get within 1 hour or half an hour. It takes time. You should practice, yeah. Then only it is possible. Please explain what is that 100. Where is 100? It is not 100, yaar. It is not 100. It is 100. In x direction it is 1, y direction it is 0, z direction it is 0. It is not 100. 100. Direction. In x direction length is 1, y is 0, z is 0. That's why this is the direction. In x direction 1 unit length I am locating. Okay, right. See, Rahul Sharma, listen carefully. In ferromagnetic material, initially it is increases, then after reaching paramagnetic material, it starts decreasing. That I am not explaining everything. After paramagnetic material, that means it's a Curie temperature, it's a para, it's a ferro. Right to decrease, okay? Increase and decrease. Toughness is an extrinsic property, depends on the dimensions, but modulus of toughness is an intrinsic property. Modulus of toughness is an intrinsic property independent of dimensions. Toughness is an extrinsic property that depends on the dimension. We can't say, like you take a steel, we can't say the toughness value of a steel. You can't say the toughness value of aluminum, but we can say exactly modulus of toughness of steel. Per unit volume of particular steel, what is the toughness? That is modulus of toughness. Okay. Right. Leave sometimes UPSC, sometimes UPSC give you like that only. At least in one paper, some 2-3 questions of UPSC is wrong. We can't say that. We can't do anything regarding that. We should work hard, we should practice, and then it should go. Next. Okay, now I'm going to end the class. Everyone satisfied? Within 3 hours, I complete everything. Just revision it and go through the original notes also, previous notes also. Go through it. We just practice that. So can you repeat ferro and ferri? See, listen carefully. Ferromagnetic material, ferrimagnetic material concept is same. But in ferromagnetic material, all the dipoles are aligned in the same direction. But in ferri, dipoles are anti-parallel. But they are not in the same magnitude. Listen here in a simple way, I'll explain. Listen. In ferro, I'll discuss later. In ferro, all the dipoles are in the same order like this. So very large magnetization, very, very high. In ferri also, most of the dipoles are in the same direction, but anti-parallel with unequal magnitudes. See, this is in this direction, these two are in this direction, this is in this direction, these two are in this direction. These are going to be cancelled out. So that means magnetization of ferri is somewhat less than magnetization of ferro. Magnetization of ferri is somewhat less than ferro. That's why in the graphs also I give like this. MH graphs or BH graphs. MH graphs if you take, this is ferro, this is ferri, this is para, this is dia, this is vacuum, right? This is anti-ferro. Okay, ferro is more than ferri. Advantage of ferri is low eddy current losses. Because of low eddy current losses, resistivity is low. Because of that, we are using for high frequency applications. High frequency applications like transformer course, 11,000 kilovolts transformer is there. From 11,000 to 1100, if you want to reduce the voltage, you can go for this because heat generation is less, because eddy current losses are less. Right. Yes, deep learn class. I think I was not explained through live class, right? This subject. I think they are given deep learn. So go to the deep learn also. What's the point of eddy current? Actually, eddy current is nothing but, for example, listen carefully. This is a material. Now I'm applying magnetic field to this material, north and south. Because of applying magnetic field, magnetic flux lines are moving. It's a magnetic force. And this is a material like you can take iron material. Number of valence electrons it is having, large valence electrons. So because of that, what is happening in the material? Electrons are moving perpendicular to this magnetic flow. Eddy current it is. That means generally energy can either be created or be destroyed, right? When the magnetic flow is present, perpendicular to the magnetic flow, by electrons using that magnetic energy and moving perpendicular to the magnetic flow. It's a loss. We don't want this eddy current, but it is generating here. That is useful in the maintenance engineering. I explained that eddy current method is used to find the defects. Right. Ferrite above Curie temperature convert into para. Correct. Ferrites above Curie temperature convert into para. Important to cover in composites, you just go through there are 3 types of composites. Just go through the composites. Classification of composites, you go to that. Within the classification, very important ones are glass fiber reinforced polymer, carbon fiber reinforced polymer, ceramic fiber, aramid fiber reinforced polymer. What is important within in the glass fiber reinforced polymer? What is the reinforcement phase? Glass. What is the matrix phase? Polymer. Okay. In the CRP, what is the reinforcement phase? Carbon. And what is the matrix phase? Polymer. Okay. In AFRP, aramid fiber reinforced polymer, what is the reinforcement phase? Aramid. What is the matrix phase? Polymer. You have to remember these things. And applications also you remember. In glass fiber, one important application you remember, optical fiber. In communication, we are using this optical fiber. In CFRP, in CFRP, Kalam Sat, you remember, Kalam Sat recently in 2017 or 18, one student from the Tamil Nadu, 12th class students, he was prepared the Kalam Sat. It's the least weight of the satellite is only 60 grams. 60 grams. That satellite is made by using the CFRP, carbon fiber reinforced polymer. And also we are using this in sports goods. And also we are using in aeroplane parts. Okay. And aramid fiber reinforced polymer. This is used as a bulletproof jacket. And also you can write defense. You just go through these things. Okay. Right. Right. Okay. Shall I end the class now? I'm going to end the class, right? Right. Okay. Good. I'll upload this today only. Now only if it is possible. I upload this one. Okay. Right.